Hello everyone. Today we are going to discuss the numerical problems that are based on Gauss theorem and applications of Gauss theorem. The numerical problems plays an important role in physics as they clears most of the concept of the physics. So let us start with the first problem of the day. As per the question, the electric field in a region is given by this. The unit is Newton per Coulomb, or I can write it as volt per meter, and there is an area of 20 units in xy plane. So if I will draw this xy plane, let me take this as x, this axis as y, and this axis as z. So my area will be in xy plane, and suppose this is the xy plane, so my area will be something like this. This is my area in xy plane. Now, since you know that the flux is E dot ds vector, so we need to calculate the area vector for this area that is on the xy plane. If I will draw a normal, that will be outwards to this xy plane, and this will be the direction of z axis. So I can write my ds vector as 20 k cap, since the unit vector along the z axis is k cap. Now since the area is known, electric field is known, so I will apply this formula to calculate the electric flux, and that will be 6I cap plus 3j cap plus 4k cap dot 20 k cap, which on simplifying gives me 80 units. So whenever such kind of problems are given, just try to find out the area vector and use this formula to find out the flux associated with that surface. As per the second question, we are having a cylinder kept in a field, and the electric field is in the direction of its axis. Now our task is to show that the net electric flux associated with this cylinder is zero, since we know from the applications of Gauss theorem that this cylinder is having three surfaces. One is this circular surface, the other one is left circular surface, and the third one is curved surface of the cylinder. So I will take area vectors on these three surfaces. For this surface, area vector will be normally outwards. For this surface, area vector will be normally outwards, and for this surface, let it is ds3, the area vector will be normally outwards. Now since the electric field is directed along its axis, so the electric field will also be along the axis here also, and the electric field at this surface will also be along this surface. So the total flux is the sum of the flux from these three surfaces. So I will write flux as the sum of the flux through these three surfaces. For this first surface, we can write the flux as E dot ds1. For the second one, once again I will write E dot ds2, and for the third one we will write E dot ds3. Since the electric field is uniform, so its value will not change through this cylinder, and it will be same as E everywhere along the axis of the dipole that I have taken towards right. Now for this surface, the field and area vector both are in the same direction, so it will be ds1 cos 0. For this surface, since electric field and area vector are normal to each other, so this is going to be E ds2 cos 90. That will give me the 0 result, because the value of cos 90 is 0. And for this one, since both are in the opposite direction, so I will write this as E ds 3 cos 180. Since both these surfaces will have the same area, so I can write it as EA. Let me, the total area of this circular surface is A, so it will also be A. So this is going to be EA. This is 0, and for this the value of cos 180 is -1. So the flux is inward. So this case we will write minus of EA, and the net flux is 0. So this was the solution to this problem. As per the next question, we have a cube of side A with the charge Q placed at its center. Now, since the cube is a closed surface, so we can apply the Gauss theorem directly, and which says that the net outward flux is the enclosed charge divided by epsilon naught. Since in this case the net charge enclosed by this surface is Q, so the flux that will come out from this cube will be Q by epsilon naught. Now, since the cube has 6 faces, so the flux from each face will be 1/6 the total flux through this cube, and it will leave the result as Q by 6 epsilon naught. So this is the flux from each face, that is the 1/6 of the total flux. Now what will happen if I will place the charge not inside this cube but on the surface of this cube? So let us see here. This is my cube. Now the charge is placed over here. You can assume the geometry of the charge as a point sphere. So first of all, we need to enclose this charge, because to apply Gauss theorem, my charge must be inside a closed surface. So I will just place a same cube just right to this, and we will have in that case so if I will place a similar cube to the right of this one, now my charge is completely closed. So the net flux through this system of these two cubes will be, as per Gauss theorem, charge enclosed by epsilon naught. So this is the total flux through these two cubes. Now if I need to calculate the flux through single cube, then I will just divide it by 2, since this is the flux through 2 cubes. So from 1 cube it will be 1 by 2 Q by epsilon naught. And similar to previous one, if I need to calculate the flux through the one face of 1 cube, so this is the flux through 1 cube, and for the face, you know that a cube is having 6 faces, so I will just take the 1/6 of the flux from 1 cube, and which will give you the result as 1 by 12 Q by epsilon naught. Now, what will happen if my charge is placed at one of the corner of the cube? Now this is your task. Just try it and find out the flux through cube and the flux through each face of the cube. Now the next question says that we have a charge that is placed at the center of a semi-spherical surface. So the charge is Q and that is placed at its center. We need to find the flux through this semi-spherical surface. So as I told you that first of all we need to close this charge. So I will make the remaining half portion of this semi-spherical surface, and now my charge is closed. these two portions are equal in area and similar in shapes, so will be 1 by epsilon naught times the charge. Since the flux is required through this semi-hemispherical surface, so the flux for my surface will be the half of the total flux. Now for the next question, first of all, we are having two concentric cells. The charge Q is at the common center and the second charge is in between these two cells S1 and S2, and we need to find out the ratio of the flux through this cell S1 and this cell S2. So as per the Gauss theorem, the flux through this cell S1 will be the 1 by epsilon naught times the charge enclosed within the cell, and the charge enclosed within this cell S1 is Q. Similarly, you can calculate the flux through this shell S2 as the charge inside this S2 is 2Q as well as this Q also. So the total charge will be 2Q plus Q. So the net charge is going to be 2Q plus Q and divided by epsilon naught, which gives 3Q by epsilon naught, and as the ratio is required, so you can write flux through S1 divided by flux through S2. So this is Q by epsilon naught divided by 3Q by epsilon naught, and that gives the result as 1 by 3. Now the second part is that if you will introduce a dielectric medium of dielectric constant K inside this cell S1, then what will be the effect on its flux? So for that, we need to see the definition of the flux, and that tells that flux is E dot ds. If you will introduce a dielectric constant, we know that the field will definitely change, and the change of field, let me take the electric field as E dash. So you know that the electric field in a medium is equal to the electric field in air divided by K. It means if I will write this equation for air, it will be E dot ds divided by K. This term is the term when there was no medium. It means there was air or vacuum inside the cell, and the flux as per the Gauss theorem was charge divided by epsilon naught. So by this formula, this is the value of integral E dot ds. Now because of this dielectric constant K, it will be divisible by K, so I will write it like this. So my flux through this cell S1 will be now Q by epsilon naught into 1 by K, and that was also the condition in the case of Coulomb's law when there was a medium between the charges. Now the third part says that if the dielectric is filled in this surface between S1 and S2, then what will be the change in flux through this cell S1, as there is no dielectric present for this cell S1 for the third case. So if there is no dielectric inside this cell S1, and you know that the flux depends on the charge inside the cell, so my flux will remain the same in the third case when the dielectric is filled in this space, but definitely the flux through this cell S2 will change as this dielectric is inside this cell. Now the next question says that a charge of Q by 2 is placed at the center of this spherical conducting shell, another charge Q on its surface, and a charge of 2Q at a distance of x from the center of this conducting shell. We need to find the force on this charge Q by 2 and the charge 2Q placed at a distance of x. So as we know that if it is a conducting shell, so the electric field inside it must be 0, and the force, since force is Q times the electric field, since electric field is 0, so the force on Q by 2 charge must be 0. Now to calculate the force on this charge 2Q, we know that for a shell, if it is a charge on its surface, then it behaves like it is placed at its center, and we have learned this concept before. So this charge, for this point charge outside the shell, this will behave as it is placed at its center, or you can say it will produce the electric field here same as it produces when it is placed at its center. So now the total charge at the center will be this charge plus Q by 2, which will be 3Q by 2. So for this 2Q charge, the total charge of 3Q by 2 will be effective at a distance of x and placed at this point. So for force, you need to calculate the charge multiplied by electric field. My charge is 2Q, and the field due to this charge at a distance x, you know, K times the charge divided by the square of distance. So if you will simplify, you will get K times 3Q square by x square. Now the third part says that what will be the flux through this shell. So as the Gauss theorem states that flux through a shell is the charge enclosed divided by epsilon naught. In this case, inside the cell, the charge of Q by 2 is here. So I will place the charge as Q by 2, which will give me this result. So that is the flux through this spherical shell. For the next question, we have a shell, and inside this cell there is a wire of length L and charge density lambda. Now we need to find out the total flux through this spherical cell. So for that we need to find out the charge on this rod L. So for that I will take a small segment here on this wire at a distance of x from one end, and let this element is dx, and let us assume that the charge on this is dq. So from the concept of linear charge density, if I divide the charge by the length, I will get the linear charge density, and that will give me the amount of charge as lambda dx. So this is the small amount of charge on this small portion of the rod. If I need to calculate the net charge on this rod of length L, I will simply integrate this charge as it is a continuous charge distribution. So dq is lambda dx. As per question, the charge density varies as lambda is equal to kx, so I will put the value here, and this is going to be integration of kx dx. And if I need the total charge, I will put the limits from 0 to L, because at this point the length is 0 and for this point the length is L. And if I will simplify this, I will get net charge as kx square by 2 within the limits 0 to L, which on simplifying gives me kl square by 2. So this is the net charge inside this cell, and now it's very simple that flux is net charge inside the cell divided by epsilon naught. So if you will put the value, you will get kl square by 2 epsilon naught, and this is the flux that will pass out through this spherical shell. For the next question, we have a cube and it is placed like this. Let initially the distance of this cube from this origin O as A and the side of the cube as A, as it is given that electric field along the x-axis varies as alpha x, while the electric field along y-axis and along z-axis is 0. So you can just assume that the electric field is only along the x-axis. But it is not a constant electric field, it varies with the distance from this center O. So, as you can see that my cube is having 6 faces, but the flux will only pass through these 2 faces, because for this face, if I will draw the normal, that is parallel to the electric field. For this surface, the electric field is along x-axis, but if you will draw the area vector is normally outward, so it will be in this direction. Now, if I will do it for this upper surface, the area vector will be normally outwards, but the field is along the x-axis and the angle between these two is 90, and we know that from the concept that if area vector and field are normal to each other, then there is no flux associated with that surface, and this will be true for all the 4 faces. It means only these 2 faces will contribute in the calculation of electric flux, while the flux through rest 4 surface will be 0. So first of all, I will calculate the flux for this surface 1. Since we know that flux is E dot ds, and here the negative flux will be there because the angle between E and ds is 180, we have seen in the previous one. So this is going to be minus electric field at a distance of A from this origin can be calculated by this relation. This is alpha times x means A and the direction is I cap, since the field is along x-axis. For this surface area, I will write area of this face of cube is A square, we know, and the unit vector I cap. I have already taken minus sign here, that's why I am not writing minus I cap. So if you will simplify it, you will get minus of alpha A cube, and that will be the flux through this surface 1. For the surface 2, we will do the same thing. Now my second surface is at a distance of A plus this distance A, that means at a distance of 2A from this origin. So I will replace x by 2A. So my electric field will be alpha 2A I cap dot area vector is A square is the area and it is along x-axis, so I will write I cap, and that will result 2 alpha A cube. So these are the flux from surface 1 and surface 2, and if you need to calculate the net flux, you need to add these two, and that will give you minus of alpha A cube plus twice of alpha A cube. So this is going to be alpha A cube. This is the net flux through this cube. Now, if I need to find out the enclosed charge within this cube, so I will apply the statement of Gauss theorem that says that flux is 1 by epsilon naught times the charge enclosed. So my charge enclosed will be epsilon naught times the total flux. We have the total flux here, so this is going to be epsilon naught alpha A cube. This is the total charge enclosed. For this situation, you can place the value of alpha, you can place the value of alpha as given in the question, you can place the side as given in the question, and you can find out the numerical value of flux as well as the charge enclosed. Now the next question says that we have two infinitely long straight wires placed at a distance of r, and these two wires have charge density lambda 1 and lambda 2, and we need to find out the force between these two wires, as they are like charges, so they will definitely repel each other. So for that, first of all, consider that this wire is producing some electric field at a point P, that is at a distance of x from this wire. So we can easily calculate it with the help of the Gauss theorem, that field due to an infinitely long wire is twice lambda by r. Here my lambda is lambda 1, so I can write it as k times twice of lambda 1 by r. Now this is the electric field produced by this wire at this point. Now my second wire is placed in this electric field, and we know that if a charge is placed in electric field, definitely it will experience a force. So if I want to calculate the force on the second wire, so you know that force F is charge multiplied by field. My field is E at this point, but the charge is not known since it is an infinitely long wire. So I will not find force, I will find force per unit length. So it will be charge per unit length multiplied by E. This charge per unit length is nothing but the charge density of this wire, and that is lambda 2. So this is lambda 2 into E, and let me take this force as F. Now I will use the value of E. So force per unit length will be K times twice lambda 1 lambda 2 by R. So this is the force that will act per unit length of the second wire. If I am interested in finding the direction of this wire, so this is the positive wire. So positive wire and this positive wire, or you can say that this positive wire will produce an electric field in this direction, and the force for the positive charge is same in the direction of field. So this is the force on this second wire. As per Newton's third law, if this wire is producing a force F on this wire, it will also produce a same kind of force but in the opposite direction. So these two forces are equal in magnitude and opposite in nature. Now if one charge is negatively charged, that is like this, and the other one is positively charged, the separation is same, then the force per unit length on both the wires will remain the same. But as you know that unlike charges attracts each other, so the direction of the force will be like this.